Hi everyone! In this video we're going to talk about derivatives of two variable functions, and those derivatives are actually called partial derivatives. And so if you think about how we have worked with functions of one variable, like f of x, when we find the derivative, we usually represent that with the notation f prime of x. And that derivative is representing the instantaneous rate of change of our function f as x changes. Now, when we're working with these functions of two variables that are of the form f of x, y, it's going to be very helpful for us to examine how the function changes with respect to just one of its variables. And so this is where we're actually going to need to use partial differentiation, which to partial differentiate, we are differentiating with respect to one of the variables and keeping the other variable fixed. So first thing, before we get into any examples or how to do partial differentiation, we need to know notation. So when are we being asked to find these partial derivatives? And so I have this little box here. So you can read through this, but the biggest part of the notation that I want to reference here is that when we write our d's in this fancy way, I'm not exactly sure what the formal term of it is, but it's different from our print d's that we used to describe the derivative. So when we see a d in this form, it's going to tell us that we're taking the partial derivative of our function f with respect to x. So still very similar notation, very similar in what it's saying, but this script d is telling us that it is a partial derivative we're finding. And this can also be represented with f sub x. So this same thing, we're taking the partial derivative of our function f with respect to x. All right, so why are we doing this? What does partial differentiation tell us? So it allows us to calculate the slope of a tangent line at a specific point. And just like we've done with differentiation of one variable functions, we can also interpret that value as a rate of change. And so to think of a case in which we actually would need to use partial differentiation, let's consider if we had a function that showed temperature readings at different altitudes up a mountain and times afternoon. And so in this case, our temperature is dependent on two different variables: the altitudes at which we've collected that temperature reading and the time after noon that it was collected. And so here we could see how the temperature changes with respect to the altitude alone. So in that case, we'd be taking the partial derivative with respect to the altitude, or seeing how the temperature changes with respect to the time after noon. So in that case, we take the partial derivative of our function with respect to the variable that's representing the time after noon. So that's a case that we would use partial differentiation. So let's go ahead and find some partial derivatives with example 1. The function f of x, y equal to x to the fourth power, y to the fourth power, plus x squared, y cubed, minus x, y squared, minus y. We're asked to determine f sub x and f sub y. So remember, looking at a first, this is the notation that we use to say we're finding the partial derivative of our function f with respect to x. So essentially what we're going to do here is we're going to pretend that every time we see a y, it's really just some number, some constant. And then we're going to go ahead and take the derivative of each term with respect to x. So looking at our first term, we have x to the fourth power, y to the fourth power. So remember, this y to the fourth power, we can treat it as just some number. So we could pretend it's a coefficient of our x to the fourth power. So what we would do is we would take the derivative of this x to the fourth power, which is 4x cubed using the power rule. And then we still have this constant there. So still multiplied by y to the fourth power. Taking the derivative of the second term with respect to x, again, using the power rule because we're pretending y is a constant. So we have the derivative of x squared is positive 2x, and it's still times this y cubed. The derivative of negative xy squared, well, the derivative of negative x with respect to x is negative 1, and then we still have that times this y squared. And then our last term is negative y. And because in this case, since we're only taking the derivative with respect to x, this term is actually just a constant. And so remember that the derivative of a constant is 0. So we have found our partial derivative of f with respect to x. So then part B, we're looking for the partial derivative of f with respect to y. So now we're going to do the same thing, except now we're saying that x is going to be our constant and the derivative is always going to be taken in respect to y. So it's very similar. So here we get, for our first term, the derivative of that y term there is 4y cubed, still times this x to the fourth power. Next term has a derivative of 3y squared, again, still times that x squared. Then we have negative y squared, which has a derivative of negative 2yx. And then here, the derivative of just negative y is negative 1. So there we have found our partial derivatives. All right, so one thing that I want to point out is that in this example, I used the power rule, which is something that we use for differentiation with one variable functions. So the rules for differentiation of one variable functions actually also hold for when we're differentiating two variable functions with respect to one of the variables. And so you can do the sum and difference rules, the power rule, the product and quotient rule, and the chain rule. All of these will apply when we're taking partial derivatives. So that's also something that you need to be careful about, because when we apply like the product, the quotient, and the chain rule, we're wanting to apply that based only on the variable we're considering. So we're only basing it on x if we're finding the partial derivative with respect to x, or we're only basing it on y when we're looking for the partial derivative of f with respect to y. So be careful about applying those rules correctly for the variables that we're concerned with. So let's actually take a look at an example. So here we have the function f of xy equals y times sine of x squared. So this time we actually are going to need to apply one of those rules that I just talked about, and namely it's going to be the chain rule here. So we're asked to determine the partial derivative of f with respect to x. And so to do this, I'm going to just rewrite this with notation. So taking the partial derivative of our function y sine of x squared, and again, we're doing that with respect to just the variable x. So I can apply the constant multiple rule. So since y in this case is treated as a constant, we can actually pull that out of this derivative, this partial derivative. So we have y times the partial derivative with respect to x of sine of x squared. All right, so now here we're going to need to apply the chain rule. So we have the derivative of sine of x squared with respect to x is going to be cosine of x squared. But then we also have to multiply that by the partial derivative with respect to x of what's inside these parentheses, or inside of our function here, which is x squared. And so evaluating this partial derivative, Well, the derivative of x squared is 2x. So we end up getting y times cosine of x squared times 2x. So again, here we applied the constant multiple rule first, then we applied the chain rule, and then we just simplified. Example 3, we are asked to determine the partial derivative of z with respect to y of the function below by differentiating implicitly. And our function is x squared plus 2xz plus y squared z squared minus z cubed equals 4. Now, first thing I want to highlight is this term differentiating implicitly. So this is actually something that we had discussed in Calculus 1 with one variable functions. So if you would like to have a refresher on that, you are always welcome to explore that resource on the website. But now we're going to use implicit differentiation with our partial derivatives of two variable functions. And so one thing that tells me that I'm going to need implicit differentiation is the use of z in our equation. So now we no longer just have x and y, z is in there as well. And so it's being multiplied, it's being raised to powers, and it's being added with the variables x and y. So to use implicit differentiation, it's going to be very similar to the process that we did above, but now we're going to have to use some chain rules because of the reliance of z being a function of x and y. So we're going to need to use that chain rule every time we encounter a term with z. So first I'm going to rewrite this. So x squared plus 2xz plus y squared z squared minus z cubed equals 4. All right, so the very first term that I need to differentiate with respect to y, so again, that means that we're holding x to be constant or fixed. So the derivative of this first term with respect to y, there are no y's, it's just an x term, and so therefore it is going to have a derivative of 0. And then the next term we have is positive 2xz. And so in this case, we don't have any y's, but we do have a z, which is a function of y. And so therefore, here we're going to have to take the derivative of this term again with respect to y. So what's going to happen is we're still going to have this 2x, but now it's going to be times the partial derivative of z with respect to y. So again, we held the x constant, we took the derivative of z with respect to y, the partial derivative of z with respect to y. Now the next term is a little bit trickier because we have y squared z squared. So therefore we have a term of y with a z, which again is a function in terms of y. And so here is where we're going to have to use both the product rule and the chain rule. And so here, first thing is using the product rule, take the derivative of the first part. So y squared with respect to y, that derivative is 2y times z squared. And then plus, we leave that y squared, and now we take the derivative of z squared with respect to y. So here is where we need that chain rule. So the derivative of z squared is 2z, but then we also need z, the partial derivative of that with respect to y, which is just going to be written as this expression there. Here we've applied the product rule and the chain rule. And then our very last term on this side of our equal sign is negative z cubed. And so here again we have z, which does depend on y, and so therefore we're going to have to use the chain rule. So the derivative of this term negative z cubed is going to be negative 3z squared, but then also applying the chain rule we get the partial derivative of z with respect to y. And then lastly we have this equals the constant 4, we still have to take the partial derivative of 4 with respect to y, which, again, using the constant rule, is going to equal 0. All right, so now the next step in our implicit differentiation is we need to combine all the terms that have this partial of z with respect to y in it. And so I'm going to underline those right now. So we're going to combine those together. So I can factor out this partial derivative of z with respect to y. And so when I do, what we have is 2x plus y squared 2z, and then minus 3z squared. And then we still have this term plus 2yz squared and equals 0. So again, we're trying to solve for this partial derivative of z with respect to y. And so we're trying to get this all by itself. And so the very first thing is I need to get rid of this positive 2yz squared. So I subtract it from both sides. So just rewriting everything else that I had. And now this equals a negative 2yz squared. Not done quite yet because this term is being multiplied by what's in brackets here. So we're going to divide by what's in brackets here on both sides. And so when we do, we get the partial derivative of z with respect to y is equal to negative 2yz squared all over 2x plus y squared 2z minus 3z squared. And so there we have completed our implicit differentiation. All right, so that is all that I have. So don't forget all of your rules that you have for differentiation with respect to one variable functions also apply to two variable functions. Just be careful that you are doing it with respect to the one variable of interest and then holding the other variable fixed. So I hope you find this video helpful, and I wish you luck as you calculate your partial derivatives of two variable functions.